Welcome students, this is 7th lecture in the continuation of the previous discussion, single phase system, where we were trying to define the various power terms and components. In the previous class, we have learnt that how to express instantaneous power for system where the voltage and current contains the DC component and the harmonics. And last time we have learnt that for this system where B and the voltage and the current both contains the harmonics, so it is BDC root 2 Bn sine n omega t minus phi Bn. Okay, and the current we have expressed similar to this IDC plus n is equal to 1 to infinity root 2 In sine n omega t minus phi In. Remember? And based on that, we have developed the instantaneous power P by multiplying these two products Bt and It, which has resulted in various important components. We have defined these terms PDC, DC and plus PDC, AC plus P AC DC and plus PAC AC. And PACC have been defined into two parts. It was PAC AC NN, similar frequency, PAC AC NH. Do you remember all these expressions? Okay, and after that, this is also defined again two parts similar to previous discussion. It is called P active, so AC NN active, and this is called P AC NN reactive. And if you go further, we will see that this gives the concept of capital P, this gives the concept of the term of the Q, okay, and these terms, that is this term, this term, this term and this term, they contribute to actually rest of the powers. So if we look carefully, then these together forms kind of an active power, because this is also a similar frequency component, DC into DC. This is AC into AC of same frequency. This is DC into DC. Okay, so it basically combines into the active part and reactive part and rest of the part. So the whole expression can be written as PT equal to P active plus P reactive plus P rest. Okay, P active P reactive and P rest. Now, what is in the P active? P active is kind of a unidirectional power. So this has two components. This is P DC plus P active. Actually, this is not just P active, it is the part of the whole thing. So you can say this is P AC NN active. And then this is P reactive, P AC NN reactive. And then plus P rest. And you know most of them, what is P rest, what is PDCAC. So PDC nothing but the product of PDC into IDC. You know it. So this is BDC into IDC. What is ACAC? Active. We proved last time. When n is 1 to infinity, this is Vn In cos phi n 1 minus cos 2 n omega t minus phi Bn. Close this bracket. This is P active. And then comes plus P reactive. So this is P reactive. So sigma minus sign will come here because it contains minus Bin. So this is a minus sign. N is equal to 1 to infinity again. This is Bn In sin phi n 1 minus sine 2n omega t minus phi Bn. This is the value of P active, total P active. Okay, because this forms this component and this forms this component. Then comes plus P rest. So this is over. Okay, because this is nothing but P reactive. So this is P reactive, which is this part. And also this must map to this part, which map to this part. And this is two parts, DC plus this one. The remaining is P rest. So P rest is nothing but all the remaining parts of the P, that is BDC into IAC. So this is BDC into sigma of 1 to infinity root 2 In sine n omega t minus phi In. Okay, this into plus IDC sigma n is 1 to infinity root 2 Bn sine n omega t minus phi Bn. This is the second part of the P rest, and the third part is the remaining of the dissimilar frequency term of AC quantities. So this means sigma n is 1 to infinity root 2 Vn sine n omega t minus phi Bn into whole thing sigma h is equal to 1 to infinity root 2 IH sine h omega t minus phi I h. This form the P rest. So this is P rest. P rest has come to this part. All this is P rest. Okay, this all thing is P rest. So what is P rest in terms of the components? The pair is P rest is, this is P DC AC plus this is P AC DC and this is plus P AC AC and H, and this is P DC DC actually already you know it, and this is P AC AC and then active and reactive. Okay, so this is complete analysis of the instantaneous power. After that, we are interested to know the what about the real power. Okay, so we are now trying to find out the real power, or you can say average power, capital P. Now by fundamental definition of real power, the P is nothing but simply Pt dt 0 to t and 1 by t. If you do this, you will easily get that this power is equal to V1, if you look it carefully from the previous expressions here. Okay, this is P. So I will take the average value of this P, this term. So when I take average value, all will be 0 except DC component. So this will be there and this will be there because 1 is there. The rest are only sine and cosine terms. And the average value of sine cosine terms will be equal to 0, whether it is omega t or 2 omega t or 3 omega t. Any multiple of omega, average value will be 0 for sine and cosine terms. So obviously this is nothing but sigma n is equal to 1 to infinity Vn In cos phi n. Something is missed out. I think that we have left actually PDC DC. So what we have left out is basically P DC DC means BDC into IDC. So we have to remove this and put simply PDC BDC into IDC plus this. This is what is real power. And if we say that real components are very less, then this will be equal to B1 I1 cos phi 1 plus B2 I2 cos phi 2, and this goes on till we get some other terms like Bn In cos phi n. Of course, BDC plus BDC into IDC will be also there, but you can always add them theoretically. But since BDC and the QDC is IDC is very small, so normally we ignore them. Okay, if you want we can put it, it's not a big problem. BDC IDC plus B1 I1 cos phi1 plus B2 I2 cos phi2 and plus Bn In cos phi n till Bn In cos phi n. Interesting? This is what, when someone asks you what is the power, real power in case of the system having harmonics, so you simply say B1 I1 cos phi 1 plus B2 I2 cos phi 2. Basically, we add all the active power formed by the individual harmonic component. So again, to continue this discussion, we can write this, that therefore this is equal to, the first part is actually PDC, so you can write simply PDC. Then next part is because of fundamental, so I'll put P1. The next part is because of second harmonic, so plus P2. Okay, this goes on till you have a PH. So H means hth harmonic component. Okay, now since PDC is normally very small, so we can neglect PDCs for close to 0. So we can write simply P1 plus P2 plus P3 and so on plus Pn or PH, you can say, to, sorry, not, this is not capital H, it should be a N actually, N is better word, so that we can vary the N later on. Okay, so we can say this is capital Pn, or we can write simply sigma Pn, where N is from 1 to capital N. Clear? This is mostly written in the form of P1 plus PH. Now, what is the relationship between this P1, PH and these expressions? It's very simple actually. Obviously, this is P1, then this must be sigma N is equal to 2 to infinity or to capital N PH, Pn. So this implies that pH is nothing but harmonic active power because of the non-fundamental components. So it is P2 plus P3 plus P4 and so on plus PHN. Clear? So the harmonic power is formed from the non-fundamental components. So these all are harmonic components. Okay, this is very important expression. Please remember this. We will use for this the power factor definition. So this is the real power. Clear? Now let us come to the reactive power. Reactive power by definition is the peak value of the P reactive. Okay, so by definition we can write the reactive power Q, by definition Q equal to peak value of the P reactive. In this case, it is the summation of this all powers. So this is Bn In sine phi n, where n varies from 1 to infinity. From where it has come? It has come from this component, Bn In here, Bn In sine. This is peak value of P reactive. It is similar to what we have done for single phase system. Okay, so this is the peak value of for each harmonic component, and then we sum, because it is a series, as there are another component, so they will be summed up to make this power as reactive power. So if we expand further, negative sign is not being considered to define it. It becomes minus B1 I1 sine phi 1 it becomes B1 I1 sine phi 1 plus B2 I2 sine phi 2 until Bn In sine phi n. So you can write this as summation from n is equal to 1 to capital N, if you want, Bn In sine phi n. Now what are these components? If we look into harmonic wise, this becomes Q1, this becomes Q2, and so on till becomes Qn. This Q2 to Qn are known as harmonic reactive power. So this is Q1 plus QH. Okay, this is total Q. And Q1 is B1 I1 cos phi 1, and QH is nothing but sigma n is equal to 2 to infinity Bn In sine phi 1. This make it sine phi 1, not cos phi 1. By mistake I put it cos phi. We get cos phi 1, sine phi 1. I am doing this mistake. Sine phi 1, this is sine phi n, where n varies from 1 to 2 to infinity. Okay, this power is also called as Boudinot's reactive power. I will explain it later on also. This definition of reactive power, that it is the summation of all the peak values of the individual harmonics. Okay, sometimes this is denoted as Boudinot's reactive power. We will see it later. Okay, so now we have defined P and we have defined Q. The next definition that we will define is the apparent power S. Okay, now apparent power S is basically product of RMS values of the voltage and currents. So apparent power, if we find out, then it is defined by S, it is product of P into I, which means basically B RMS into I RMS. Okay, now B RMS is nothing but B1 square. In fact, BDC square, if we neglect BDC, we can leave it. Otherwise, this is B1 square plus B2 square plus so and so on plus Bn square and if we want to take BDC as well, then we can add the BDC. So we will add it here equal to BDC square. The whole thing is square root into IDC square plus I1 square, so on till IN square. This is also square root. This is the RMS value of voltage and current, and their product is here. Now, if we go further on these lines, then we can say this is BDC square plus B1 square plus BH square. Into square root IDC square plus I1 square plus IH square. Now what is BH square? What is the IH square? Obviously BH is the harmonic RMS value, and this is the square root of, or you can say VH square is sigma V n square, where n is equal to 1 to n. This is small n here, so make it small n, 1 to n. Small n here. And similarly, the value is I h square is same as sigma n is 1 to infinity or 1 to n I n square. Okay. We can also say that I1 IH or IBH represents the effective harmonic component in its RMS values. Okay, because this will also lead to the fact that BH is nothing but the square root of V2 square plus B3 square and so on. Similarly, IH is nothing but I2 square plus I3 square and so on. Okay, so basically they represent the total RMS value of the harmonic content, BH and IH. We have used the term capital H. Okay, so capital indicates that it is the total value of RMS value representing the harmonics. Now once we know these quantities, then we can further expand them to find out what is the value of S. Okay, so for that we have to further expand these terms. Obviously we have to multiply them and arrange in a certain order. For example, this can be multiplied and square both the sides. That's S square equal to VDC square into IDC square, like this. Okay, then we will have BDC square, and then the remaining is I1 square plus IH square, two terms of the current. So BDC into this, and then comes B1 square plus B1 square, I1 square plus B1 square, IDC square, you can say. B1 square and then IDC square plus B1 square into IH square. and then we have plus BH square IH square plus BH square IDC square plus BH square into I1 square. So there are 9 terms because there are 3 into 3, 9 terms will come into picture when you multiply them. Interestingly, there is straightforward choice to select them. For example, this is very important for me. This is the fundamental apparent power square. This is the similar frequency interaction. Okay, IBDC into IDC. Similarly, BH into IH. The rest are all combinations. So I will put in the form of the fundamental and non-fundamental in this particular case. Okay. For example, we can write this here as S B1 square into I1 square. First term. And then we'll put as BH square IH square. Only harmonic interaction, this one. The remaining have BDC and BDC into I1 and all those components are there. Okay. Now if we neglect the BDC is very small, so BDC square IDC square then plus BDC square here I1 square plus BDC square IH square, 3 terms, and there are more 4 terms, 3 plus 4, 7 plus 2, 9. Okay. The other terms plus B1 square IDC square plus B2 square IH square and then plus BH square IDC square plus BH square I1 square. Okay. Now since BDC is very small, so we can neglect them to 0. So all this DC component, if you want, you can simply say they are very, very small and hence they can be ignored. And therefore, finally we have I1 square plus BH square IH square plus, this is not B2, this is B1, I1 square into BH square. Okay, and this together forms the apparent power from non-fundamental terms, these 3 components. They have been given special names when we compute the apparent power. For example, this is called fundamental apparent power S1 square. And then this is called harmonic apparent power. Therefore, SH square. These 2 powers are called as distortion powers because these have been coming from the distorted current or voltage interacting the fundamental of the other. For example, this is B1 square into IH square. So this distortion is because of IH. Therefore, this is called DI square. And this is distortion because of the voltage. This is called distortion apparent power because of the voltage. And this is total S square. Clear? So these four components make the total apparent power S. This is very important expression, and this will be used later on to find out the value of the power factor. Okay, so this is further simplified in form of the S1 and the Ph.D components. How this is being done? We will define the Ph.D component of voltage and current. For example, Ph.D voltage defined as VHY V1. Do you remember this expression, this definition? The Ph.D total harmonic distortion. Total harmonic distortion. Ph.D in voltage defined by the harmonic RMS value of the voltage VH divided by V1. This is also equal to sigma Vn square, n is equal to 2 to infinity, you can say, and 1 by 2. So this is nothing but Vh, and divide by V1. Similarly, the Ph.D in current is written as IHY I1. Okay? IHY I1. Therefore, we can express from this BH in terms of Ph.D V into V1, and IH can be expressed into Ph.D I into I1. These two values are used in this expression back. Okay, then we can find out, we use this, therefore S square equal to, this is S1 square. Now SH is equal to VH into IH square, so this becomes Ph.D V square into V1 square into I1 square into Ph.D I square, because there are two Ph.Ds here, so I will remove this, put total term together. So I will put it here, this one, Ph.D I square into V1 square into I1 square. This is the SH square. Then plus DI square. DI is V1 square into IH square. So IH is Ph.D I square. This is Ph.D I square into V1 square into I1 square. Okay. So this becomes V1 square into I1 square. This becomes distortion apparent power because of current Di square. And the last term is nothing but Ph.D V square into V1 square I1 square. And this is already V1 square I1 square. Clear? This is by default I1 square V square. I won't put S1 right now. System is very slow, I think. So this becomes V1 square and I1 square. What do you see from this? that many B1 I1 square term is common in this all. So if I take common B1 square I1 square, what will we get? 1 plus TST I square TST voltage square plus TSD voltage square and TSD I square, the whole thing equal to S square. And this is nothing but S1 square. So this is S1 square, if you want to write this way, plus or into, bracket if you want, this becomes into here 1 plus TST I square TST B square plus TSD I square and TSD B square. Or S equal to S1 1 plus TSD I square plus TSD B square plus TSD B and I square. The whole thing is square root of this. So you see that S is S1 times of this factor. And this factor is certainly greater than 1 if there are harmonic content in the voltage and currents. Then THD I or THDB will be greater than 1. Okay, so the apparent power will be greater than the fundamental apparent power, obviously. Sometimes these terms are denoted as non-fundamental apparent power. So this term, which I have used earlier, can also be expressed as S square equal to S1 square plus Sn square. You got it? What I am saying, the S square term, which earlier we used as S1 square plus SH square plus DI square plus DB square is expressed as S1 square plus Sn square, where Sn square is nothing but summation of non-fundamental apparent powers. And S1 square you already know, B1 square into I1 square. Okay, so this is another interpretation normally used to represent the overall apparent power S square or S. So it's clear now that we have derived the expression for P, for Q, for S. Okay, then we can find out the important term of the system, power factor. Power factor is, as I said, a ratio of P by V to S. And you know what is P in this particular case. P1 is nothing but P1 plus PH. And S is nothing but S1 1 plus TSD B square TSD I square plus TSD B square and TSD I square and square root of this. Okay, take common P1 from here, So becomes 1 plus Ph by P1 into P1, take S1 up, so P1 by S1 divide by 1 plus Ph.D. V square plus Ph.D. I square plus Ph.D. B square Ph.D. I square, the whole square root. Okay. And what is this? This component. P1 by S1. This is cos phi 1. This is the fundamental power factor. We call it displacement power factor. So this can be further written as 1 plus Ph by P1 divided by 1 plus Tsd V square plus Tsd I square plus Tsd B and I square. The whole thing square root here, and this is Pf1 or cos phi 1. That is power factor 1, fundamental power factor. This is called fundamental power factor. Or displacement power factor. Okay, and this is very interesting relationship. So this relation says that the overall power factor cos phi is function of the pH component of power and P1 and the THD components of the voltage and currents into fundamental power factor cos phi 1. You may be thinking, what about the value of this factor? Is it equal to 1 or it is less than 1 or it is greater than 1? On what condition it depends. Okay, so that we will see in the next class. It depends upon the load pattern, the harmonic components of voltage and currents. Alternatively, we can express this relationship in terms of the voltage and current RMS values and the impedance parameter, the load impedance parameters. So we will see in the next class and will comment upon the value of this factor, that how the overall power factor cos phi varies as a function of cos phi 1, including the component inside this factor. See you in the next class.